Hello everyone and welcome back to thermodynamics subject. Today we will start chapter 3 of the course and we will discuss about the properties of pure substance. This chapter is very important chapter, especially for future chapters. You will learn more about the substances which we have for thermodynamic system. So actually, this chapter is basic chapter for uh, most of the uh, uh, future chapters of this subject as well. So let's begin to see what will be in this chapter and what are the objectives and also the subtopic for this chapter. First of all, I should say to you about the textbook for this chapter. As usual, this chapter is based on this book, Thermodynamics and Engineering Approach. It's 8th edition, which is written by Dr. Sanjal and his colleagues. So this chapter also is chapter 3 of your textbook. This textbook, you can find more information about this chapter in this textbook. The objectives of this chapter, as you can see also in this slide, are first I will start with an introduction about the concept of a pure substance. You will see what is a pure substance, how we can distinguish between pure and non-pure substances. Then we will discuss about the physics of phase change processes. Before that, I will introduce you the different phases of the material. However, it is just elementary things, and I think you are aware about them. But I just briefly review some important. Uh, I will just review some important information about these different phases. Then we will go for to see what are the different diagrams for to see the relationship between the phases of the material and temperature, specific volume, and the pressure are these properties. What is the relationship between these properties and the phase of the phases of the materials or the substances? Up to here, we will cover in this session, and rest of this, which is about demonstration of the procedure for determining the thermodynamics properties by using different tables, describe the description and describing the hypothetical substances as ideal gas, and uh, the ideal gas equation of a state will be another topic which will be for next session. Then also we will use some equation related to this ideal gas to state the solution of typical problem related to these different substances. I will introduce some concept as well like compressibility factor, and also we will see how we can use some best known equations of the state for different problems. So now let's start to with the first topic, which is an introduction about the concept of pure substance. What is pure substance? According to the definition, pure substance is a substance that has a fixed chemical composition throughout whole substance. So this is important, if you just, notice to this definition, you can distinguish between the pure substance and non-pure substances. Some examples of pure substances are water, nitrogen, helium, and carbon dioxide, which all of these these substances are pure substances. These pure substances, however, not always does not have to be of a single chemical element or compound. It can be a mixture of different elements. A mixture of various chemical elements or compounds also qualifies as a pure substance as long as the mixture is homogeneous. This is the condition to have a pure substance as a mixture as a pure substance. In other words, the chemical composition of uh, that mixture should be homogeneous in the whole area of that mixture. For example, air is a mixture of several gases, but it is often considered to be a pure substance because it has a uniform chemical composition. Here is an interesting example of a mixture, a material which is a mixture of different gases, but still we can consider it as a pure substance because the chemical composition in each point of this material is identical to other point of that material. So we call that a pure substance because it has a uniform chemical composition. And on the other hand, a mixture of oil and water is not a pure substance. Again, here we have a mixture, oil and water. But if you notice, when you mix oil and water, oil is not soluble in water. It will collect on top of water, forming two chemically dissimilar regions. So we have a border which separates the two material which are mixed to each other. Actually, they cannot uh, mix to each other, and we have a border. And mm, however, we can call it a mixture, but the chemical composition in different point of this mixture is different. Some part of that is only water, and on top of that is oil. So this mixture is not a pure substance. So you can see differences between mixture, which one is pure substance and which one is not a pure substance. And also a mixture of two or more phases of the pure substance is still a pure substance, as long as the chemical composition of all phases is the same. A good example for this, when we have one substance but in different phases, when we can call that mixture of that different phases for that material as a pure substance, as long as the chemical composition of all phases is the same. Like what? Like a mixture of ice and liquid water, which the composition of the chemical composition for both of them is H2O, and we have in all part, here we have that mixture of one substance, which is liquid, and which is water, or H2O, but in two different phases. If you notice here, chemical composition is H2O, here is also H2O. But on the other hand, we have another example for a mixture of one substance, one material in different phases. But because the chemical composition for different phases is different, then we cannot call that uh, as a pure substance. Like what we have here, a liquid phase of air and a gas phase of air, or usually we call that air. So why we cannot call this as a pure substance, this mixture as a pure substance? Because air is a mixture of different gases. You can see here, just here is just a illustration of the some of the gases in the air mixture. You can see here it consists nitrogen, oxygen, argon, carbon dioxide, even vapor, and also other gases. You can see also some of the percentage for these gases. And if we, if we just liquidify the air by pressure, by increase the pressure and other method, you know, the gases which be liquefied will be different in different pressure. I mean, not all of the gases which are in the air when it is gas will be in the liquid phase. It depends on the pressure and other conditions which this air is uh, changed to the liquid, or from gas is changed to liquid. I mean, the chemical composition for the air will be different from this one, from the liquid air. So a mixture of liquid air and gaseous air, however, is not a pure substance, since the composition of liquid air is different from the composition of gaseous air, and thus the mixture is no longer chemically homogeneous. The first condition to consider if a mixture is pure substance or not. And I told you about its reason: different component in air condensing at different temperature at a specified pressure. So the uh, gases, the type of gases or material in the liquid air is different from the gas air. Let's continue our discussion to uh, about the phase of a pure substance. This part may be maybe just brief review for you, because I think many of you know about the phases of the material. We have three different principal phases for different material: solid, liquid, and gas, which under different conditions may one substance may appear in different phases. For example, water or H2O can be gas as vapor, can be liquid as water, or can be solid as ice. So you can see here one substance can have different phases in different conditions. Also, a substance may have several phases within a principal phase, each with a different molecular structure. The meaning of this sentence is about in one phase we have different molecular structure of one material. A good example for this is carbon. Carbon, when it is in solid phase, it has two different distinct structure. It can be graphite or diamond in the solid phase. So in just one phase, it can have two different structure. This is just an example. And also about the helium. Helium has two liquid phases. Iron has three solid phases. Ice may exist at seven different phases at high pressures. You can see here that also in these three principal phases, we have other structural phases between these, each one of them. But the important things you should know is about three basic or principal phases: solid, liquid, and gas. We will have more discussion about them, they are defined, and how we can distinguish them. Usually it is easy to distinguish them, but sometimes it's not that much easy to find the border for the to distinguish between the liquid or vapor and so on. We will see some examples about that. And also we have a definition for phase. A phase is identified as having a distinct molecular arrangement that is homogeneous throughout and separated from the others by easily identifiable boundary surfaces. Like here, for example, we have, according to this definition for the phase, here we have a good example when we have a glass of a mixture of water or liquid H2O and ice or solid H2O. We can find the border and boundary for the ice as the solid phase with the liquid phase. And the molecular structure for the solid is different from the water. So each one of them is in one phase. This one, the ice is solid, and water is in the liquid. The border is distinguishable, and also the molecular structure is different. Now we will see, however, this molecular structure, as you can see here, for solid, liquid, and gases. And gas is not that much important for thermodynamics, this molecular structure, because usually we do not go in detail to study this molecular structure. What we are interested about in thermodynamics is only the phase which they have, and the molecular forces and so on is not that much important in thermodynamics. And in our calculation also, it is not that much important. Only the phase and the pressure and temperature and other properties for that phase is important for us. Then we can distinguish, we can find the energy for that and so on. But here I just briefly let you know what is the differences between molecular structure for different phases of material, what is the structure, molecular structure of solid, liquid, and gases, what is the differences between them. Let's start with the solid phase. The molecules in a solid are arranged in a three-dimensional pattern that is repeated throughout, like what we have here in this uh, figure. You can see a simple illustration of the solid phase. They have a pattern, and they are arranged in three-dimensional pattern, and which is repeated throughout whole substance. This is solid phase. And as you can see here, these molecules are fixed, and because of the small distance between them, the forces between the molecules is very high and does not let the molecules to move, and their position is fixed. And this force is very high, and it is preventing the molecule from building up on top of each other. So their position is fixed, and they cannot even move their position or even shift their position. Even though the molecules in a solid cannot move relative to each other, they continually oscillate about their equilibrium position. So the only movement or motion for the molecules is oscillation for the molecule in solid phase. The velocity of molecules during this oscillation depends on the temperature. So this small movement, the oscillation, here you can see that oscillation, which is like a spring. They can just, shift their, in this distance, they can oscillate, and or even this distance, but the position will be fixed. This oscillation, the rate or the velocity of this oscillation depends on the temperature of the substance. As much as temperature is higher, this oscillation velocity will be higher as well. And in sufficiently high temperature, the velocity and thus the momentum of the molecules may reach a point where the intermolecular forces are partially overcome and groups of molecules break away. In other words, this motion, because of the thermal energy, will be in higher velocity than some molecules or some part of molecules can break these high uh, mm, forces, molecular forces, and they can break this structure. This is beginning of melting process. So because of the temperature and increase the motion of the molecules, these molecules can break this structure and it is a start of melting. Then the phase, it is actually a start of changing phase from solid to liquid. Now let's see what is the liquid phase. The molecular spacing in the liquid phase is not much different from that of solid phase. What it means, the molecular spacing, it means the space between the molecules, as you can see here, they are still close to each other, the molecules. So their space is still, or distance between the molecules is still same as the solid, except the molecules are no longer at fixed position relative to each other, and they can rotate and translate freely, like what you can see here. If you compare this figure with what we had for the solid, in solid you can see they have a pattern. They have a three-dimensional pattern, but in liquid phase we don't have that, and the molecules can rotate, can rotate to each other. They can change their position, but still space between molecules is constant, and they cannot go away from each other. The space is same, but they can rotate around each other and translate freely from one point to another. In a liquid, the intermolecular forces is weaker relative to the solid. So we have still a strong force between the molecules in liquid, but this force in the liquid phase compared to solid phase is lower. So the molecules cannot easily, in the liquid phase, they cannot separate from each other. So they have to still stay in constant space to each other. And this intermolecular force is for the liquid is less than or weaker than the solids molecules, but it is stronger than the intermolecular forces which we have in gases. And as I told you, the distance between molecules generally experiences slight increases as a solid turns liquid. As I told you in previous slide, when temperature is increased, the oscillation in the solid, the velocity of oscillation will be higher than in a specific temperature. This oscillation will be high enough to break down some part of that intermolecular forces. Then it starts to melting, and this melting means change from solid phase to liquid phase. However, the phase is changed, but still there will be a fixed space between the molecules. But this fixed space for the liquid phase is a little bigger than the space which we have for solid phase. Then the volume of a material when their phase is changed from solid to liquid will increase. We have an exception, which is water. Water, when a phase of water is changed from solid to liquid, its uh, volume is decreased. It has some chemical reasons which is out of our scope of this subject. You can refer to the chemical or physics textbook to know more about why water is the exception, why its volume is uh, decreased when it phase change from the solid to liquid, and why it's and vice versa as well. And next let's see what is the gas phase. In the gas phase, the molecules are far apart from each other and the molecular order is non-existent. So molecules can freely move and their motion doesn't follow any pattern. Their position is not fixed, the molecules, as you can see here, and they constantly are colliding to each other, and also the boundary of the the part or anything which they are this gas is inside that border. Gas molecules move about at random, continually colliding with each other and the walls of container they are in. Particularly at low densities, the intermolecular forces are very small, and collision are the only mode of interaction between the molecules. So you can see differences between these molecules are really free. They can go anywhere in the container, and when the density is very low, the intermolecular force is also very low. Molecules in the gas phase are not a considerably higher energy level than they are in liquid or solid phase. So energy of molecules in gas phase is much higher than energy in the solid or liquid. Therefore, the gas must release a large amount of energy before it can condense or freeze. So if you compare the structure, the molecular structure of the gas with liquid or solid, you can see to have a phase change from gas to liquid or solid, we need to catch this molecule to put there in the fixed position. For example, to change from gas to solid, or to uh, we need to reduce their energy and keep in just a fixed position and let them to rotate to around each other to change from gas to liquid. This means we need to absorb energy from them. High amount of energy should be absorbed from the gas to change its phase, or from gas to the liquid or solid, and it is just illustrated in this past slide why we need to absorb energy from the gas phase to change its phase from gas to liquid or solid. What is the phase change process? Phase change process means the uh, the phase of a substance is changed from one of those three principal phases to each other to another phase. There are many practical situations where two phases of a pure substance coexist in equilibrium condition. So even we have that phase change, we have some conditions which we have uh, both or any other, or even three of those phases for a substance together. They are coexist in an equilibrium condition. For example, water exists as a mixture of liquid and vapor in the boiler and the condenser of a steam power plant. So in the boiler, we have a mixture of the liquid and vapor. In the boiler and in the condenser, it is a mixture of both of the substance, both phases, gas and liquid for this substance in these two equipment. So in this section, in next few slides, we will see what is happening when a phase of material is changed, and how its molecular structure is changed, how will be the pressure, temperature of the substance during these phase changes. To have a better understanding about this phase changing process, I will explain to you these phase changes, this phase changing for water as a as an example of the pure substances. And but you need to remember all pure substances exhibit the same general behavior like what I will explain for water. In other words, what I will tell you about the phase change, their diagram, and so on is for water, but the process will be same also for other pure substances. However, the values, the numbers, temperatures, pressure may be different, but the process will be same for all other substances, pure substances as well. Okay, now I will explain to you how this phase change process occur, is occurring for a uh, pure substance, and we will see different state during this phase change process. So we imagine an imaginary experiment like what we have here. We have a cylinder. Inside that cylinder, we have water, and we also put weight as a piston on top of the water inside the cylinder. Also, we have a thermal energy or heat source in bottom of this cylinder. The initial temperature of the water is 20 degrees Celsius, and pressure of the water here is 1 atmosphere because it is free to the atmosphere, so and it is in sea level, so the pressure for the water here is 1 atmosphere. And as you know, in this situation, with this condition, the phase of the water will be liquid, and we have liquid H2O or water in this condition. So first consider a piston cylinder device containing liquid water at 20 degrees Celsius and 1 atmosphere pressure, like what we have here. Under this condition, water exists in liquid phase, and it is called compressed liquid. So when in this condition, we call the water in the state of compressed liquid or a subcooled liquid, meaning that it is not uh, about to vaporize. So subcooled or compressed liquid means a liquid which is not about to vaporize. An important definition, which is one of the states for the pure substance. So compressed liquid or subcooled liquid, meaning that the liquid which is not about to vaporize. Then, as time is passing, this thermal energy or heat is transferred to the water inside the cylinder. It is now transferred to the water until its temperature rises to say, for example, 40 degrees Celsius. So its temperature then increase because of this temperature, which is absorbed by the water, and it comes from the heat source. Temperature is increased from 20 degrees Celsius to 40 degrees Celsius. Then, as this temperature is increasing, the liquid water also expands slightly, and so its specific volume will increase. So, because of this increase in the temperature, the volume of the water also will increase. To accommodate this expansion, the piston moves up slightly, so the position of this piston compared to the initial position will be higher. The pressure in the cylinder remains constant at 1 atmosphere during this process since it depends on the outside barometric pressure and the weight of the piston, both of which are constant. So we are going to have a constant pressure process here. So when the because we don't have any changes for the pressure and it is free to move this piston. When the volume is changed, if uh, the position of this piston was fixed, because the volume is going to change but it cannot change, then the pressure will increase. But here, because the pressure is constant, because the volume can increase without any resistance, then pressure will be constant. Why the pressure is constant? Because the pressure which the forces actually are acting on the border of this uh, substance or water are the weight of this piston and atmospheric pressure, which both of them are constant during this process. And this pressure is 1 atmosphere. Still, water is still a compressed liquid at this stage since it has not started to vaporize. Even at 40 degrees Celsius, it is subcooled or compressed liquid because it is not about to vaporize. If we increase the temperature of the water to 100 degrees Celsius, at this point the water is still in liquid phase, but any heat addition will cause some of the liquid to vaporize. Until this 100 degrees Celsius, only temperature of the water or liquid water is increasing. Then when the temperature of the water reach this 100 degrees Celsius, more than that 100 degrees Celsius, or actually the temperature that will not change. Only the thermal energy which is absorbed will cause the uh, phase changing for the substance, which is water here. So at when the temperature of water reaches 100 degrees Celsius, any extra thermal energy or heat will cause a phase change from liquid or will cause, separation of some of the H2 molecule from liquid to the surrounding or changing phase from the liquid to gas, from water to the vapor. This is a phase change process from liquid to vapor, and it is about to take place at 100 degrees Celsius. So if we just reach the 100 degrees Celsius, this phase change process is about to happen, not happening actually. To have a phase changing, we need to have a flow of energy like what we have here also after we reach this 100 degrees Celsius. A liquid that is about to vaporize is called a saturated liquid. For example, water in these conditions, pressure 1 atmosphere and temperature 100 degrees Celsius, is a saturated liquid. It is about to vaporize. So therefore, the state 2 is this state is saturated liquid state. Then, if we continue this heat addition to this uh, system, water inside this cylinder, the boiling will start. Boiling means changing from the phase of liquid to gas. The temperature stops rising until the liquid is completely vaporized. In other words, when the temperature of the water inside the cylinder reach 100 degrees Celsius, after that the thermal energy or heat which come to the system will not increase the temperature of the water. It just cause phase changing. It will cause more molecules run away from the liquid or water to the vapor phase. This process, this separation of the molecule from liquid to the vapor phase, will continue until all of the molecules in the water are transferred to the vapor. And in other words, all of the molecule of the water is vaporized. The temperature will remain constant during the entire phase change process. This is important, and later we will see why it is important. If the pressure is held constant, this is also important condition. These happen, these remaining constant value for temperature will happen if we have a constant pressure. Here we have constant pressure because this uh, weight is free to the atmosphere and it can freely move, so the pressure on this substance will be constant during process. During a boiling process, the only change we will observe is a large increase in the volume and a steady decline in the liquid level as a result of more liquid turning to vapor. I think which is clear. More liquid will convert to the vapor, so the phase of vapor will increase. Then the space between the molecules of the substance will increase. Then volume is increased, and also the amount of liquid will lower because the more molecule is shifted from the liquid to the vapor. And about the vaporization line, the cylinder contains equal amount of liquid and vapor. What we have here, this is a midway of the vaporization line. What we have here, we will have an equal amount of liquid and vapor. This is state 3. We have saturated vapor and saturated liquid. We will have another definition for this, which is saturated liquid. This one is saturated liquid and vapor mixture. As we continue transferring heat, the vaporization process continues until the last drop of liquid vaporizes. Then we have only vapor inside the cylinder. At this point, the entire cylinder is filled with the vapor. Any heat loss from this vapor will cause some of the vapor to condense, phase change from gas to the liquid. Vapor that is about to condense is called saturated vapor, like what we have here. In this condition, pressure 1 atmosphere, temperature 100 degrees Celsius, and phase is vapor. If we reduce the temperature, even if we stop this flow of energy to the system, the molecule will start to convert from vapor to the liquid. So this state is saturated vapor, a vapor that is about to condense. A substance at the state between these two, this is saturated vapor, whole vapor about to condense, and also saturated liquid, a liquid about to vapor. Between these two, we have saturated liquid vapor mixture, since the liquid and vapor phase coexist in equilibrium at this state, like what we have here. So this is a state between the state of the saturated liquid and saturated vapor. We call that saturated liquid vapor mixture. There is chance for both of the direction, from liquid to gas, from gas to liquid. Because of that, we call that saturated liquid vapor mixture. Let's go back to our example. If temperature, here temperature which is still 100 degrees Celsius, and all of the water or liquid water is um, changed to the vapor. Then if we continue this warming up of this cylinder, temperature of the vapor will be higher, will increase. So, this is after that phase change process. Then we continue to warm up this cylinder. Then temperature of the vapor will increase from 100 degrees Celsius to above. For example, here in stage 5, we have 300 degrees Celsius. And during this, you can see the specific volume of the vapor is also changed. If we transfer some heat from the vapor, the temperature may drop somewhat, but no condensation will take place as long as the temperature remain about 100 degrees Celsius. So in this state, if we reduce temperature from 300 to 250, still we don't have any phase change. And the substance is not about, the vapor is not about to condense. So it is not a saturated vapor. This state, which is a vapor that is not about to condense, in other words, it is not a super saturated vapor, is called a superheated vapor. So superheated vapor is a vapor that is not about to condense. Very important definition. Superheated vapor, vapor which is not about to condense. Even we reduce the temperature, it will not condense. So this is the superheated vapor. This is a phase change process from the liquid to the vapor. As you can see, in different phase, we had 5 different states to explain these different phases, and also we have seen superheated, saturated vapor, saturated liquid vapor mixture, and saturated liquid and subcooled or compressed liquid region as well. If we are going to show this process, this phase changing process from liquid to the vapor, you on a T V diagram or temperature and specific volume diagram, you can see here we have started with temperature of 20 degrees Celsius and the volume was V1 and is T 20 degrees Celsius. Then we increase the temperature. Now you can see here during this phase, still we are in the this phase, which is compressed liquid, until it reach this temperature 100 degrees Celsius. During this process 1 to 2, we have increasing the temperature, and we have also increasing the volume, specific volume of the water. Then from the process 2 to 3, we have a saturated mixture. During this process, temperature will be constant, and the energy, thermal energy, which comes to the system is for phase change process. So the phase change process actually is happening in this uh, step, in this process 2 to 3, and 3 to 4 also is just continuing. The temperature is constant. More the this is saturated vapor, and this is saturated mixture. Then this is for a stage 5, which we had this process. We have superheated vapor. You can see here the volume is increasing, and the temperature also is increased. If you remember, we had this temperature was increased from 100 to 300 degrees Celsius. We continue to add more thermal energy to the water or to the vapor. We have superheated vapor here. And you should notice this line, this curve, which shows this process on TV diagram, this the phase change process on the TV diagram, is for constant pressure, which was 1 atmosphere. This is the illustration of the process we had for the phase change from liquid to the vapor for water as the example for pure substance. And you can see here different uh, phases and also different region: compressed liquid, saturated mixture. Here's saturated vapor and superheated vapor. You can see changes of temperature and volume also in these diagrams. These diagrams are important, and we will use these diagrams. We will use these diagrams to explain the different phase change process for different material by this diagram, because it is easy to understand to how is the relationship between temperature, volume, and pressure, uh, and phases of a substance. The process which I have explained here, with adding of the thermal energy or heat to the water, and that phase changing in a constant pressure, can be in reverse direction. I mean, from superheated vapor to the subcooled liquid by getting or by cooling that superheating, then uh, saturated vapor until we reach the subcooled. Only the same amount of energy should be captured from the uh, substance which we have here. And also, you should notice that usually in daily life we call the liquid water as water, and we call the water in vapor phase as steam. But in thermodynamics we call that H2O. No differences between them, and we usually just call them as H2O in our calculation and problem. Then, according to the uh, definition which we uh, have already about this phase changing, then we can define two other properties, which are a saturation temperature and saturation pressure. The temperature at which water starts boiling depends on the pressure. Therefore, if the pressure is fixed, so is the boiling temperature. In other words, these what I told you about those phase changes, and also about the diagram about the values, is depends also to the it depends on the pressure as well. So strictly speaking, the statement water boils at 100 degrees Celsius is right. Please try to memorize and try to understand this sentence. It is important, and it is a big mistake which we may do in our daily life, which the boiling point of water is 100 degrees Celsius. We don't have this sentence, and we cannot use this sentence without uh, stating of the pressure. Water boils at 100 degrees Celsius at 1 atmosphere pressure. So the boiling point of water, as an example for pure substance, is dependent on the pressure. So we have a relationship between the pressure and temperature. As here also we have that the graph for that, and also we have two different definition for the temperature and pressure, which this phase changing is starting. Saturation temperature, or TSAT, is the temperature at which a pure substance changes phase at a given pressure. So the temperature at a given pressure. We should know both of this. How much is the pressure? Then we can distinguish or to find the temperature with this phase changing is happening. Then we can call that saturation temperature. And saturation pressure, or PSAT, is the pressure at which a pure substance changes phase at a given temperature. So from now on, anytime you are discussing about the boiling temperature for a substance or a pure substance, actually, you should know, or you should ask about the pressure which this process is happening for that. For example, uh, the mm, simple example is about the water. Water is not boiling in 100 degrees Celsius in all of the areas, for example. You may have some experiences about that, or you may experience that in higher elevation, water will boil faster, or in lower temperature. This is because of the lower pressure in lower pressure or atmospheric pressure in higher elevation. And you can see here a relationship between the saturation pressure and saturation pressure and saturation temperature. And you can see here, as much as the saturation pressure is increased, saturation temperature also is increased. In other words, if pressure is increased, the temperature with which water starts to boil, it will be also higher. And in this table 3.1, you can see saturation or boiling pressure of water at various temperatures. You can see here when the pressure is 0.26 uh, kilopascal, water will boil at negative 10 degrees Celsius. You may haven't experienced something like this, but it means if we remove the pressure from water in a chamber, it will start to freeze. Its phase change. This means less than 0 degrees Celsius. It means it will be it will produce ice in that vacuum chamber. So you can see here, and also when the saturation pressure or the pressure on that water is 8,588 kilopascal, the boiling temperature will be 300 degrees Celsius. And this is important to design some interesting equipment like pressure cooker. I will introduce you, and I will present you a video to show how we can use these interesting characteristics between the pressure and boiling point to be an intelligent chef, and how to use a pressure cooker, and how is the principle for a working of a uh, pressure cooker. However, you may use this equipment in your kitchen, but you may have not noticed how is the principle of working for this equipment, which is very useful equipment or device. And here you can see also how some simple basics or knowledge can help to design something very useful. Here is a real application of this concept, the relationship between the saturation pressure and saturation temperature, and you can see a real application of these phenomena. So let's see this video, which is explaining what is happening in the pressure cooker.
Under normal conditions, water boils at 100 degrees Celsius, and that's as hot as it's going to get. The same rule applies to the water that makes up most of our food. It can't get hotter than the boiling point. And this limits how quickly food can cook. A pressure cooker raises the speed limit. Liquid is placed inside the pot with food, sealed in by a specially designed lid, and heated to the boiling point. Trapped and unable to keep expanding, vapors build up the pressure inside the pot. When this builds up to the cooker's target pressure, usually about twice normal atmospheric pressure, excess vapor is allowed to escape. Because of the increased pressure, liquid water in the cooker will stay liquid at a higher temperature than its normal boiling point of 100 degrees Celsius. And not just the water around the food. The water molecules inside the food will also become hotter than they could under normal pressure. As a rule, for every 5 degrees Celsius that the temperature increases above 100, the cooking time is cut in half. So an increase in the water's boiling point of just 20 degrees Celsius accelerates cooking speed by up to 16 times. pressurized cooking environment allows chefs to soften hard artichokes and legumes, quickly transform tough beef chuck into succulent pot roasts, and, in minutes, cook dishes that can take hours with traditional cooking methods. Once the food's finished, the cooker cools until the pressure returns to normal. Then it's time to taste the spectacular flavors that develop using this remarkable cooking method.
As you have seen also in the examples, and as you have seen in the process which I told you about, that uh, phase changing, phase changing required energy gaining or energy gain or energy loss from the uh, substance. So without changing the energy of the substance, we don't have also a phase change. Latent heat is the amount of energy absorbed or released during a phase change process. We have a specific name for that, and you have seen that this, why we have this, because if you notice in the graph as well, uh, during phase changing process, the whole energy which come to the system or come to the substance is being used to phase changing. So we call that latent heat, the amount of energy which is absorbed or released during a phase change process. Latent heat of fusion is the amount of energy absorbed during melting. So for this phase change process, we have a specific name of the latent heat for this phase changing process or melting, and it is equivalent to the amount of energy released during freezing. If you notice, the melting and freezing are two contrary uh, phase changing processes, and the energy which is absorbed by the system by the substance during melting is equal to the energy which we should take or release from the system during freezing. Melting is in opposite of the freezing. And latent heat of vaporization is the amount of energy absorbed during vaporization, and it is equivalent to the energy released during condensation. Condensation means a phase change from the gas to the liquid, and vaporization means phase change from the uh, liquid to the vapor. The energy required for these phase changes is latent heat of vaporization, which is equal for these two opposite processes or phase changes process. And the magnitudes of latent heats depends on the temperature or pressure at which the phase change occurs. Again, you can see here this energy which is required is the energy which is required. Latent heat means energy which is required for the phase change. So this energy amount of this energy is dependent on the pressure or the temperature with which this phase changing process is happening. Why? Because of that example I told you, in higher elevation, or for example in higher in lower pressure, less energy is required, for example, for vaporization, and vice versa. Higher energy is required for the condensation. So you can see here again, it depends. This latent heat is depends on the pressure and temperature which that phase change process is happening. The atmospheric pressure and thus the boiling temperature of water decreases with elevation. This is one of the reasons why in the higher elevation the vaporization process starts faster or with a less amount of energy. You can see here a relationship between the elevation from the Earth surface as a reference. Here is the atmospheric pressure at that elevation, and here is boiling temperature. You can see here elevation 0, sea level actually. The atmospheric pressure is 1 atmosphere or 101.33 kilopascal. then boiling temperature will be 100 degrees Celsius. And as long as the elevation is increased, atmospheric pressure is decreased, then boiling temperature also will decrease. It's the relationship between the pressure and boiling temperature. And simple example is the relationship between the atmospheric pressure and elevation. And some of the consequences of these saturation temperature and saturation pressure can be seen in these figures you can see here. This is the example I told you. In 1775, ice was made by evacuating the airspace uh, in a water tank. You can see here by creating a vacuum chamber, putting the water in that vacuum chamber, and removing the air. They produce ice from the water. This is one way to produce ice. Instead of getting energy, they are getting the pressure of the water. Then its will its phase will change. And also we have another example. The temperature of liquid nitrogen exposed to the atmosphere remains constant, like what we have here. The liquid temperature, the phase change for the nitrogen, we have a phase change from the liquid to gas for the nitrogen in negative 196 degrees Celsius, very cold temperature. So if we put a test chamber in this liquid, its temperature will be also constant in equilibrium condition. That test chamber also, temperature of that test chamber also will be 196 degree Celsius. So we can keep constant the temperature for the test chamber by floating the or sinking the test chamber in the uh, liquid nitrogen and insulation of that chamber. Then the temperature will be 196 degrees Celsius. This is some of the application of the relationship between temperature and pressure, or between the uh, saturation temperature and saturation pressure. You can refer to your textbook to have more explanation about these processes or applications. As I told you, and also you have seen in previous slide, the variation of the property during a phase change process can be studied by helping out by using property diagram, like temperature specific volume diagram, like pressure specific volume diagram, and PT diagram. These three types of diagrams are important, and they can completely help us to understand these phase changes processes, and also we can understand the different states of material by using this diagram. So now I will start to discuss about these diagrams for during these phase changes processes, and also for a pure substance. Okay, let me start with the TV diagram, or temperature and the specific volume of the substance, pure substance, which is here water. So let's draw a TV diagram for the water during this phase changing process, or adding this thermal energy to, or changing of the energy actually of the water or pure substance during this phase change process. First of all, this TV diagram, we have already uh, developed this diagram for during that process, which I told you about, that piston as a cylinder. We had this, this is TV diagram again. Here, the at the bottom of this graph, you can see the graph which we had. This is, this is the graph for that process. For the water during that phase change process, you can see the similarity between this and the previous uh, graph, and you can see its pressure. Now imagine we had during that phase changing process, we add some weight on the top of that piston which we had to increase that constant pressure to the 1 megapascal, for example here. So what we have done, we just added weight on top of that piston. We changed the weight actually. So during that phase change process, instead of 1 atmosphere pressure, we have a constant pressure equal to 1 megapascal. So you can see here the differences between these two graphs. This graph, which it is what we have for the uh, 1 atmosphere or 100 kilopascal or zero point zero 0.01 megapascal, and this is the graph, that graph during that phase change process for the constant pressure of 1 megapascal. You can see here the similarity and differences between these two graphs. First of all, you can see it will locate at the higher, at the top of the 100 kilopascal constant pressure, and so because the pressure during that phase change process is increased, then the graph it is located above the graph which we had for the lower pressure. This is first thing we can see in this graph. Now we will see why we have something like this. This is because of that the saturation temperature and pressure which I already introduced to you. But let's see the similarity. Again, we have those region, we had subcooled, saturated liquid, saturated vapor, superheated area. Again, we have all of those areas. Here is saturated, uh, here is superheated area, superheated. You can see this is for different pressure. As long as the pressure is increased, this graph is shifted to upper. It means the phase change is happening. For example, here is the point which the phase change from the liquid to the vapor is started. If you remember, for 1 atmosphere, it was 100 degrees Celsius. But if we change the pressure, or saturation pressure is changed, then this, for example, if it is changed to 1 megapascal, then the saturation temperature, or the temperature which the phase changing process is started from liquid to the vapor is also increased. For example, it was mentioned here 179.9 degrees Celsius. So this is the differences, and this is the reason, because we have higher pressure, so the phase changing also start in higher temperature. So temperature is higher, and also we also is changed. The specific value, the changing of the phase is started in higher specific value. In other words, until here we have still that subcooled liquid. And also the phase change, not the phase change actually, the process which we had here when the excuse me, when this state is changed from the saturated, here we have saturated uh, vapor. If you remember, in this part we had saturated vapor, and in this part we had saturated mixture. This V also is lower. In other words, the specific volume of the substance is lower when the pressure is higher for the uh, changing from the saturated uh, vapor to the superheated vapor. So this line will be shorter. This is the line which we have for the saturated mixture and saturated vapor. So you can see in higher pressure, this line, which is the phase changing line, actually will be shorter. You can see pressure is increasing, this line is shorter. And until we reach a point when this line actually is not a line, it is just a point when this phase changing is happening. We call that critical point. So let me just briefly read from the slide what I explained to you. First, let's add, we have that TV diagram for one pressure, 100 kilopascal. Now we add weight on top of that piston or on top of the water or substance which we have, the different weights, then we will have different constant pressure during that phase change process. So we will have a graph like this for TV graph for different constant pressure and phase changing for the water. Okay, the first example is 1 megapascal. This graph, as it is transferred to the water at this new pressure, the process follows a path that looks very much like the process path at 1 atmosphere. This one and this one. You can see the similarity. But there are some noticeable differences. First, water starts boiling at much higher temperature, like what you can see here. Much higher temperature. This is the start of vaporization. Second, the specific volume of the saturated liquid is larger, and the specific volume of the saturated vapor is small. These two, this is saturated liquid, this is saturated vapor. You can see here in this pressure, the difference, this line is this much, and as long as the pressure is increased, this is again saturated vapor, this is saturated liquid, again, you can see the line is shorter. So this horizontal line will be shorter. As the pressure is increased, this line will be uh, shorter. And it becomes a point when the pressure reaches 22.06 megapascal for case of water. So for water, this line will be a point at when the pressure is 22.06 megapascal. This point is called critical point, very important point when we are studying the phase changing for water, and it is defined as point at which the saturated liquid and saturated vapor states are identical. In other words, in this point, any increase in the energy will cause changing. Here we have a liquid which is about to evaporate, and also we have a vapor which is be about to condense. So instead of a line, we have a point, and in this point we have both of the saturated vapor and saturated liquid. The temperature, excuse me, the temperature, pressure, and a specific volume of a substance at the critical point are called respectively critical temperature, critical pressure (TCR) or here for critical pressure (PCR) and critical specific volume or V sub CR. So first critical point, the point which we have saturated liquid and saturated vapor, and in this point the temperature and pressure and specific volume are the critical excuse me critical value, and the critical point values for water is mentioned here. For any substance we can find these critical points in table A1, which we can find all of the critical properties, which are temperature, pressure, and specific volume in this table. Let's see what we have in table A1. In this table, table A1, you can see some properties, which what I am going to show here is critical point properties for different materials. You can see here the substance name, air, ammonia, and so on, and their formula, molar mass, gas constant. But here what is important for us for this session is that these three characteristics or properties: temperature, critical pressure, and critical volume, which is the or critical specific volume actually. These three characteristics are for the critical point when we have saturated liquid and saturated vapor for each one of these substances. This is important later for some other calculation in future chapters. And at the pressure above this critical pressure, what we have is a phase which is we cannot distinguish which the material here is vapor or liquid. So we do not have there is not a distinct phase change process. In other words, if the pressure for that substance is higher than critical pressure, we don't have a phase change process actually. We have only one phase throughout the system, and we cannot distinguish when this phase changing process happening actually. It is always changing the process, and we cannot find a process like this to have to see how is that phase changing process happening. Instead, the specific volume of the substance continually increases, and at all times there is only one phase present. As you can see here, only the volume or a specific volume of material is changing. And we cannot see, for example, like what we can see for the liquid. If you are just watching the liquid or water, it is boiling, the phase is changed, and the water liquid is will be lower and vapor will be higher, or at least you can see the amount of liquid is lower. But if the pressure in that cylinder is higher than critical pressure, you cannot see that process. You can see only the that piston is going up and up because the volume is increasing. This specific volume is increasing. Eventually, it resembles a vapor, but we can never tell when the change has occurred. So, just in you cannot uh, select or see when this phase changing is happening. Above the critical state, there is no line that separates the compressed liquid region and the superheated region, like what we have here. This is superheated, this is liquid region, but above this, we don't have a line like this. So we have for whole of this, this process, we have only one line. So it is, however, it is customary to refer to the substance as superheated vapor area at superheated vapor at temperature above the critical temperature. So this is just imaginary, and we can use this to distinguish between vapor and liquid in our calculation. So it is customary to refer to the substance as a superheated vapor at temperature above the critical. Here we call this superheated for this line. We call this superheated. However, we cannot distinguish the differences, but we have a imaginary, or we have an assumption. We call this superheated region, and as compressed liquid at temperature below the critical. We call this for, because this is the pressure higher than critical pressure, and we use this critical temperature to distinguish the superheated and uh, compressed liquid for this substance when the pressure is critical. And the saturated liquid, which we liquid state in the figure which we have already seen, connected by a line called saturated liquid line. This line, we call this line as saturated liquid line. Why we call this saturated liquid line? Because, for different pressure, imagine we have infinitive pressure. This graph, this one, it is only just for one pressure, constant pressure. Imagine we have infinitive pressure, then this point on all of those graphs, this is the point on this graph, this is the point on this graph. Imagine we have other graphs like this, and more and more graphs. Still, the point on this graph, if we connect these points to each other, we will have a line like this. Imagine we have a graph like this. This is a TV diagram. Then we have too many, graph like this for, each one of them is for constant pressure. Then if we distinguish and find the point which is for saturated liquid on that graph, we will have something like this. And if we connect this point to each other, infinitive line, it will be another line, which we call that uh, saturated liquid line, because uh, the that substance, if the temperature and the volume is equal to that point, if the temperature and volume is located on this line, it will be for sure a saturated liquid phase. So we call this line saturated liquid. And we have a similar line which we call that saturated vapor line, which is the uh, a line which connects the saturated vapor states for different pressure. So we have this line, this is the saturated vapor line, this is saturated liquid line. And you know about critical point, the point which we have both of the critical, both of the saturated vapor and saturated liquid. All the compressed liquid states are located in the region to the left of the saturated liquid. So this area is compressed liquid region, and any if the temperature and volume, a specific volume of that substance is located in this area, it means the state of that substance is compressed liquid. And if it is located at the right side of the saturated vapor line, it means it is in the superheated vapor region. And we have also another region which is in under the dome of this uh, graph, which we call that saturated liquid vapor region. So we have one region here, second here, and third region here. We have three different regions, two different lines, and the right side of this will be superheated vapor region, compressed liquid region, saturated liquid vapor region, and critical point. And these two lines, saturated liquid line, saturated vapor line. This is, and this saturated liquid vapor region also called wet region, which we have lots of the liquid and vapor in saturated state. The PV diagram, what I have told you up to here is about TV diagram or temperature and specific diagram for this phase changing process of the, and these regions also are in the TV diagram. We for the PV diagram or pressure, the relationship between the pressure and specific volume for a pure substance during that phase change process is same, and you can see PV diagram for a pure substance. The similarity between these two here, you can see better, I think. You can see the similarity. Those regions are again identical: compressed liquid region, saturated liquid vapor region, superheated vapor region, saturated liquid line, and saturated vapor line, critical point. Also, we have all of those areas in PV diagram. This is TV diagram. If you notice here, the only differences, this line is for constant pressure, this dashed line. This line is produced for infinitive lines which are constant pressure. But here, this dashed line is for constant temperature. And if you notice here, the direction is different. Uh, the T constant lines, trend of the line is downward, but here trend of the line was upward. This is the only differences between TV and PV diagram. And as you notice here, we have all of these three properties: PV and T, V and P. P is the graph inside the coordination, and here is different P and V for the axis, and this T is for the graph. You can see the differences clearly, I think, in the graphs. The other things are the same, and you just should notice that the line, the graph which shows the for a constant temperature is above the for the temperature which is higher, increase of the temperature. How we can have this PV diagram? Again, consider a piston cylinder like what we had. Again, it contains liquid water. The what and the temperature is 150 degrees Celsius. So why it is liquid water? Because temperature is 1 megapascal, not 100 kilopascal. So according to that saturation pressure temperature, when the pressure of the water is 1 megapascal, still if the temperature is 150 degrees Celsius, we don't have phase change. So still it is again uh, liquid. Water at this state exists as a compressed liquid. Now the weights on top of the piston are removed one by one so that the pressure inside the cylinder increases gradually. So we start to reduce the weight on top of this piston, then the pressure will reduce. The water is also allowed to exchange heat with the surroundings, so its temperature remains constant. So while we are removing these weights, the pressure is reducing, but the temperature is constant. Why? Because we have a heat source here, and also we have a heat exchange between the uh, water and surrounding, and this changing in the volume and changing in the pressure is happening slowly and gradually, so the temperature will be constant during this process of decreasing of the pressure. As the pressure decreases, the volume of the water increases slightly. It is reasonable while we are removing these weights. The volume will increase due to the reduction of the excuse me, due to the reduction of the pressure. When the pressure reaches the saturation pressure value at the specified temperature, the water starts to boil. If you remember, we had the saturation pressure for each temperature, and it is the pressure when the phase changing will start. So temperature is constant, but the pressure is decreasing. When pressure is decreasing, then it is gradually reaching to the saturation pressure. When it reaches saturation pressure, that phase changing process will start. You can see here, uh, this is constant temperature. This is PV diagram. Then you can see here, P is decreasing. Reduction of P, it reached here. Then the phase changing it starts. Then again you can see the volume is increasing, a specific volume here, a specific volume is increasing, but in this phase changing process we have here we don't have phase change. Here only pressure is decreasing in constant temperature, and also volume is increasing. But when it reaches here, it is the saturation pressure, and it is the pressure for this temperature for T1, which the phase changing is started. So the phase changing start here from liquid. The start to We have saturated liquid here, then it start to boil, and phase is changing from liquid to vapor during this process. In this area, the volume is increasing, but the pressure will be constant in this part. Then until all of the liquid water is vaporized. When it is evaporated, all of that, we will have a saturated vapor here. After that, if the pressure, here pressure, the reduction of pressure is continued by removing that weight, then we will have a superheated vapor region, because you can see here the volume is also increased, and just by changing of the pressure for the uh, this pure substance, you can see how the phase changing process is happening, how it experiences these different regions. So during this vaporization process, the both temperature and the pressure remain constant. It means this part, but a specific volume will change. And I told you about this part will continue until the last droplet of the water is also vaporized. And similar to the previous graph, which we had for TV diagram, again, we can have this saturated liquid line, we can have this saturated vapor line, but this time we need to, connect these points for infinitive constant temperature. And finally, we have this line and this line, and also we have critical point, which we have uh, superheated, which we have saturated liquid and saturated vapor simultaneously together in this point. These two equilibrium diagrams, which we have developed so far, represent the equilibrium state involving the liquid and vapor phases. If you notice, we had only liquid and phases. Our examples, our illustration were started with a cylinder and a piston and a heat source for water, which was liquid, then vaporization for the water, excuse me, to the vapor. So what about the phase change from solid to liquid or even solid to the gas and vice versa? However, if you remember this PV diagram, this part was for liquid and vapor. Simply, we can add solid phase to this graph. You can see here, we discuss, for example, in this PV diagram, this is for a solid, but not water. I will tell you why not water. You can see here, you know, during this process, volume will be constant. However, pressure is decreasing for this, but the volume is constant. For example, this is melt. This is ice. The pressure is reduced, but it is not that much. The pressure is not that much low to increase the temperature, for example, or the pressure is not that much low to let the molecules to change their structure, to change their position in the structure of the solid material. In this point, the melting will start, and in this area we have both of the solid and liquid. This is the melting process until it reaches here. You can see again this slide is for liquid. For liquid also volume, specific volume doesn't change with reduction of the pressure until a certain point, and after that by reduction of the pressure, this part of the graph is similar to the previous one. We have only added this part, until here to this PV graph, as you can see here. Volume constant for solid, volume constant for the liquid, and change a sudden volume or increase a volume of the solid when it is melting. This is for mm, substances. Most of the substance, the PV graph will be like this. But for some of the substance, like water, it is different. You can see here, for example, for water, when it is melting, its volume also is increasing. This is solid line for the water, which is an exceptional substance, which when it is melting from ice to water, it's you can see here volume is increased. Or here you can see differences between PV diagram for the water and other material. So this diagram can easily to be extended to include the solid phase as well as solid liquid and solid vapor saturation region, like what you can see here. most substances contract during a solidification. So when material is changing the phase from the liquid to the solid, we call that solidification. For example, freezing for the water from water to the ice. Others like water, however, this example is not good for the water because water is different. Some material like water expand as they freeze. In other words, for the water, this process is different. When they freeze, they expand. For other material, when they melt, they expand. So the PV diagram for both groups of substance are presented here. You can see differences between them, how the pressure and volume is changed during these phase changes process. This diagram differs only in the solid liquid saturation region, this part. The TU diagram looks very much like the PV diagram, especially for the substances that contract on freezing. It means this one. So this one is also can be TV diagram by changing of the pressure of the that for that substance. For example, this is the reduction of temperature, or this is the increase of the temperature, and you can see the changes. And you may notice that in some condition we have all of these three phases together. So like what we have here, we have solid, liquid, and vapor phases for just one substance in an equilibrium condition, or they are coexist in an equilibrium condition. On PV diagram or TU diagram, these triple phase states form a line called that triple line. If I go back to this, you can see this is triple line. Why we call that triple line? This is an equilibrium condition which we have solid. This is solid vapor area. This is liquid vapor area. But on this line, we have solid, liquid, and vapor together. This state on triple line of a substance have the same pressure and temperature but different specific values. The triple line appears as a point on the PT diagram and therefore it is often called the triple point. So in PT diagram, this I will show you later the PT up to now. I show you PV and TV diagram for different processes. I will also show you this PT diagram, especially to find this triple point, which is the point which we have all of the phases for a substance. The triple point temperature and the pressure of various substances are given here in this table, as you can see here. Triple point temperature and pressure of various substances. For example, for water or H2O, you can see in this temperature in terms of Kelvin, 273.16 Kelvin, and in this pressure point, 61 kilopascal, we can have ice, water, and vapor together in an equilibrium condition, which is also mentioned here. And it means in this condition we have all of three phases in equilibrium, and no substance can exist in liquid phase in a stable equilibrium at pressures below the triple point pressure. So this is a hint to understand what will be a phase of material in a specific condition. So no substance can exist in liquid phase in a stable equilibrium at pressure below the triple point pressure. We will see also in the graph. The same can be said for temperature for the substance that contract and freezing. However, the substances at high pressures can exist in the liquid phase at temperatures below triple point. Let's see the graph. This is the graph. You can see here, this is PT graph or diagram for a pure substance. You can see here, this is triple point, which we can have, this is solid area, this is vapor area, this is liquid area. So you can see how these lines are separating these three areas. And you can see also, for example, if temperature is less than this, it will be in solid area. If it is higher than this, it will be, depends on the pressure, it can be in the vapor or liquid area. So there are two ways a substance can pass from the solid to vapor phase. Up to here we discussed about phase changing from liquid to vapor, vapor to liquid. Now we are going to see how is the phase changing from solid to vapor. There is two ways. Either it melts first into a liquid and subsequently evaporates, or it evaporates directly without melting first. So first it can melt, then evaporate, or it can directly goes from solid to vapor phase. So we have two ways for this phase changing from solid to the vapor. The latter occurs at pressures below the triple point value, since a pure substance cannot exist in the liquid phase at that pressure. Means this area. It says, according to the sentence I have already read, it says we have this phase changing from solid to vapor only can happen in low pressures. Low pressure, it depends on the material. For example, for this material, the pressure less than this will cause a phase change from solid to the vapor directly. But if the pressure is here, first it should go to a melting process, then go to the vaporization, vapor phase. Passing from the solid phase directly into the vapor phase is called sublimation, what we can see also here. So this line is sublimation line crossing of the solid to vapor. This line is vaporization from liquid to the vapor, and this line is melting from solid to the liquid. But you can see here we have two different lines for the melting. This one is substances that contract for and freezing. The uh, volume is decrease and freezing, and this line is for substances that expand and freezing. When they freeze, uh, when they freeze in this direction, their physical volume will increase, like water. So we have introduced you this sublimation uh, line as well, changing phase from solid directly to the vapor. For substances that have a triple point pressure above the atmospheric pressure, such as solid CO2 or dry ice, sublimation is the only way to change from solid to vapor phase at atmospheric pressure. So it is an interesting example for the CO2 in the atmospheric pressure uh, can its phase can be changed from the solid to the vapor only in direct phase change process. So we have a vapor around the ice of the CO2. And here you can see a PVT diagram. I told you we call this phase diagram because we have all of the phases in this diagram. The sublimination line separates the solid and vapor region, and I think already I told you about the different region and different lines in this diagram. The only thing is the vaporization line ends at the critical point, this point, which is no distinction can be made between liquid and water phase above the critical point. So above this critical point, you cannot distinguish the phase of material or phase of the substance, which it is in liquid phase or in the vapor phase. So it ends in this point. And also I told you about these two dashed and solid line. So I have finished our discussion about the 2D diagram, PVTV diagram, and also finally PT or phase diagram. Now let's see if we can show this diagram in a 3D diagram. Can we have PVT diagram for a material, for a substance or not, and how it can be? Okay, now let's see a three-dimensional diagram for this phase change process. As you can see also here, we can show these phase change processes in a 3D diagram like what we have here, pressure, volume, and temperature in different coordination like what we have for X, Y, Z. Why we can do this? Because as you know, the state of a simple compressible substance is fixed by any two independent intensive properties. I have already introduced all of these words, what is intensive properties and so on. So if we know how much is volume and temperature, it is with their fixed value, then we can see how the phase of that material is changed with changing of the pressure, for example. So we can have a relationship like this, which Z here, for example, as a pressure, it is dependent on the X and Y, which are volume and temperature, for example. Then this PVT diagram will be something like this, PV and T. 3D illustration of the phase change process. Then all the point and the surface represent equilibrium state. So any point on the surface of this, it means equilibrium state. It means it reached the equilibrium condition. The material substance with that pressure and volume and temperature. All these states along the path of quasi-equilibrium process lie on the PVT surface. Since such a process must pass through equilibrium state, it is also, I think, clear. The single phase region appears as curved surface, like this solid curved surface, liquid curved surface, and you can see here all of the curved surface is for the single phase regions, and two phase regions as surfaces perpendicular to the PT plane. So we have this PT plane. If we watch this in this direction in PT plane, the surface perpendicular to this plane is the two-phase region. As you can see here, liquid, vapor, or solid vapor, which are perpendicular to the PT plane. And all the two-dimensional diagrams we have discussed so far, we can project, if we just watch this from this view to this 3D dimensional 3D graph, and project these surfaces to this plane, we will have PV diagram. From this direction, we will have PT diagram, and from the above, if we look at this, we will have a TV diagram. So if you notice here, we can have all of those information about the phase changing process, and we can distinguish the phase of the material or substance, which is the purpose of these graphs, according to the temperature, volume, and pressure. For example, if we know how much is the volume, how much is the temperature and pressure of the material, we can exactly say for that material if it is in solid phase or in liquid phase or so on, then we can find the properties for that material in that phase. But if you notice here, however, it is a comprehensive diagram. In thermodynamics, we usually just use 2D diagrams. So I'm not going to go further and discuss more about these 3D diagrams. Just you should be familiar with the structure of the diagram, and you should know that we can also show this PVT diagram like what you can see here, and also we can understand the phase of the material according to this PVT diagram. And you can see here we have two PVT diagrams. One of them, the left one, is for the matter substances which expands on freezing like water, and the right one, this one, is for the substance that contracts on freezing. So this is three-dimensional phase change process diagrams or PVT diagrams. And however, I introduced you, but usually we use just two-dimensional diagram like PV and QV. So by this slide, we reach end of this session. Next session, I will explain more about the property table, which are prepared according to the phases which I already introduced you in this session, and phase changing process which I already introduced in this video. Thank you very much for being with me in this session. I hope you have enjoyed this video. See you next session.